I do want to begin our conversation, and this is going to be a very one-sided conversation, I'm afraid, but I do want to begin our conversation by saying that there's nothing new here. You've done what we are about to do already. It's just all packaged together in a slightly different manner and has a certain level of complication, but there's nothing new. It's the same motion stuff we have already done. And ultimately, what I'm going to teach you is how to organize yourself to be able to deal with a projectile motion problem. Again, I'm giving you a method. You don't have to use my method. But I would encourage you at the beginning to use my method. When we are done, every bit of the projectile homework is available for you to complete with the information you learned today. I'm going to be looking at that homework probably being due early next week, so perhaps Tuesday. And that will complete all the kinematics, and we'll finally be able to get into real physics stuff. So, yeah.
Is that second part you were talking about yesterday?
Yeah. So I'm going to repost a due date thing with it attached in case you lost it, can't find it, or whatever. Yesterday, I outlined the beginnings of our conversation about projectiles. So today, let's start kind of with that concept in mind. I want to do this twice, once really fast to kind of just give you the overview, and then we're going to be very particular. So a projectile is any object that travels in two dimensions but experiences an acceleration in only one. Did I say that to you yesterday?
Yes.
Good. It's an out and out lie. So let me augment the lie for just a minute. A projectile is an object that travels in two dimensions whose motion can be tracked in two one-dimensional problems. That's truthfully what a projectile is. I'll say that again because that's a big complicated sentence and you may not understand it right away. So let me say it again. A projectile is an object that travels in two dimensions but can be tracked by looking at two one-dimensional problems. Now, you are of limited experience, so you don't really know what that means. Let me help you understand what that means. Because there's the easy projectile problems, which we will do. But then there's complicated projectile problems. An easy projectile problem is this one. No air and one acceleration downwards, gravity. This object I can study by breaking into two dimensions, a horizontal dimension and a vertical dimension. Only one of them is experiencing an acceleration. That's the basic problem. But you can have projectile problems that have accelerations in two dimensions. What if the wind is blowing this way? Well, then the x component gets its acceleration, and the y component gets its own acceleration. I can still study this by looking at two one-dimensional problems because each dimension is separate, has a separate acceleration. You see, what determines whether we can analyze something or not is to note the direction of the acceleration. For us to be able to analyze a problem, we can only do one-dimensional motion at a time. This will be true all year long. So, if we can break our problem up into one-dimensional problems, we can do it. So 2 accelerations isn't a problem as long as each acceleration is only in one dimension. Where this breaks down is when you have true air resistance. Air resistance opposes motion. So that would mean that if the object were here, traveling with a velocity in this direction, it would have air resistance in that direction, and air resistance is an acceleration. You understand, for a projectile, that would mean that everywhere it goes, the air drag is going to be traveling or pointing in a different direction. This problem cannot be done using the rules we're about to develop, because in this problem, the direction of the acceleration is always changing. Do you see what I'm saying? This is not a projectile problem, or at least not one that's within our capacity to solve. So we can solve a problem as long as we can break the problem up into 2 independent, one-dimensional problems. That's what allows us to solve them. And I promise you, all of yours will be like that. They will all be able to be broken up into 2 one-dimensional, independent problems. So let's take a look at that one-dimensional independent, or those 2 one-dimensional independent problems today. God, that's a lot of syllables. I don't want to say it anymore. So we're going to give our object, and this is the symbology I will use for this. Our object gets a launch velocity, which I'll call v naught. Almost always, at the start of any one of these problems, you're to assign a coordinate system, but for projectile problems, the coordinate system is almost always assumed to be a coordinate system that is aligned with the horizon, so we generally make that the x direction. And that'll be true all the time. It's whatever's parallel to the ground. That usually means that the angle, and angles are the things that provide reference, that the angle is given to you relative to the horizon. So two things constitute the start of a projectile problem: an object that is launched at some velocity and at some angle. That suggests straight away that our object will be associated with two different velocities. Because we're going to break our problem up into two different dimensions that suggest two different velocities. The first is a horizontal velocity. This is the portion of the launch velocity that's directed along the horizon. And an initial y velocity. This is a portion of the velocity that's directed in the y direction. Now, you'll notice Vx doesn't have a little naught next to it, but Vy does. First, I'm choosing x and y, I think for obvious reasons. Is it obvious to you guys? Y being vertical, x being horizontal. That all okay? The naught here is to remind you that the y velocity is going to be experiencing an acceleration. It will change. It will only have this value at launch. That's what the naught is supposed to tell you. The x doesn't have one of those because the x direction isn't experiencing an acceleration. So because it's not experiencing an acceleration, this value stays constant from the moment the object is launched until the moment the object hits the ground. So to exaggerate that a bit, considering that the path of the object is probably going to be something like that, no matter where I pick and consider looking at the object, at every one of those positions, Vx will be the same. Right? The horizontal velocity remains unchanged throughout the duration of the object's motion. So I don't want to do a lot with this, but I do think it appropriate that you consider that no matter what, that red arrow, which I'm using to represent the horizontal velocity, should always be the same. Not true for the vertical velocity. The vertical velocity is experiencing an acceleration, which means on the way up, gravity is making it go slower. So on the way up, that arrow is going to be getting smaller. And then on the way down, it's going to be getting bigger. Right? It's experiencing an acceleration. So although all of the Vx's, bless you, are the same, Vy is always changing. All good? Now, we call the distance to where the object strikes the ground the range. Technically, it's a horizontal displacement. And we will call the launch height delta y, but height is good too. So if you want to use h, fine. I'll use delta y, and I'll keep y for this whole conversation associated with vertical motion and x associated with horizontal motion. It shouldn't be too hard for you to figure out that there is a clear relationship between the initial velocity, the horizontal velocity, and the launch velocity. Do you see the relationship I'm trying to point out? Now, if you're having difficulty with it, I'm going to do something I am resigned to do, but we'll do it anyways. All right, I do want to emphasize that no matter what, the object only has one velocity. Every single time, it's just one velocity. Those components are always just telling us parts of the object's velocity. but the whole time it's moving, it has only one velocity. We're just describing this object by focusing on the horizontal and the vertical separately. That all okay? So at any time, you could find the object's absolute velocity. That would be looking at the individual components and then finding the total velocity using a vector. A little trick. Pythagorean theorem, tangent to get the angle, stuff like that. What I would encourage you to do for every single one of these problems is begin by organizing yourself. If you've paid close enough attention, you realize there are some things here that should be very familiar to you. So I am going to start all these problems the same way. Here's how I'd like you to start them. I'd like you to consider that for every problem, there's going to be a vertical portion and a horizontal portion. Based on what we just described, the vertical portion is undergoing uniform accelerated motion. So there will be 5 motion variables associated with what's happening in the vertical direction. There's going to be a delta y, a vy initial, a vy for some period of time, an acceleration, and t. All the things we have come to expect for a problem that is experiencing a uniform accelerated motion. However, you'll notice I adjusted it all, right? Put the y's in there to let us know we're talking about the vertical direction. As opposed to the horizontal. The horizontal is going to have a displacement, but it's in the horizontal direction. We call that the range. It's going to have a horizontal velocity, but there's no acceleration. Because there's no acceleration, this value doesn't change. So the only other variable to worry about is t. Now, I think this is obvious, but I'm going to say it anyways. The time it takes the object to go up and down is the same as the time it takes to go side to side. The thing that you have to realize is that every projectile motion problem is about you associating the time on one side with the time on the other. Every one of them will be something like that. And if you're really paying attention, you'll realize you must be given at least 3 pieces on the left side or 2 pieces on the right side. Right? We have a collection of equations that go with the left side. A whole bunch of them that have trained you on the idea that you only need 3 things. You can figure out the other unknowns. And we've worked this before. If there's no acceleration, when there's only one relationship that brings those 3 things together. And that's clearly going to be range equals Vx times t. If you're trying to figure out where the object hits the ground, then you're going to need the time that it's in the air. Again, a shrewd student would realize you could augment this template with some things that will help you get started faster. Right? I'm augmenting the template and adding one more thing to my template. I think this is a good template to start with. If you can flesh out this template, you can solve any projectile problem, no matter how complicated. They're all going to be associated with making good choices in this template. So let's do the basic problem, and then let's talk about some augmentations to that problem, okay? Here's the basic problem. The basic problem for projectiles is to find a range. So let's set up a basic problem. Let's say I have an object that's going to be launched off of a 2-meter high platform. And I'm trying to make this pretty basic, so let's say it's launched at 5 meters per second at an angle of 30 degrees. A basic problem would ask you to find the range. Where does it strike the ground? All right? This is a basic projectile problem. We're going to work this together. And in working this together, I'm also going to highlight something I'd like you to be able to do. I'm going to start with the template. And until you become proficient, I'd like to see you start with the template. When you're proficient, cut corners. But I think you should demonstrate your proficiency first. So vertical, horizontal, delta y, vy naught, vy, a, t. Delta x, vx, t. This is the range, and in this problem, this is the question mark. In these problems, these two sides are connected through time. Right? This is my template. So, like any motion problem, the first thing I will do is try to identify the given information and fill in the template. Now look, you're going to be given, this is similar to other problems, except you'll be flooded with information. You can't just count on knowing that if something's in meters, it only has one place to go. That's gone now, right? There's 3 different places velocities could go. And there's 2 different places displacements can go. You have to be aware and thinking about it. So this side is everything that's about the up and down part of this problem. And this side is everything that's about the side-to-side part of this problem. The object travels 2 meters downwards, right? It's starting 2 meters above the ground, so it's going to go downwards 2 meters. That's the y displacement. The object's being launched at 5 meters per second and 30 degrees. You'll notice V naught's not anywhere in there. I'm going to have to interpret the fact that although V naught is 5 meters per second and theta is 30 degrees, you have to interpret what that is going to mean. Now, I said you could augment your template, and maybe you should, but I know that's going to be 5 sine 30. If you augmented your template, you can just, write this to the side. It's in a gravitational field, we'll assume in the Earth, so 10 meters per second squared acceleration. And since I broke the velocity up into a horizontal component, I can also break it up, into a vertical component. I can also break it up into a horizontal component and write 5 cosine 30 here as well. Step 1, identify the information that has been given. I have identified the information that has been given. Step 2, I'm going to assign direction to my problem. These problems are meant to help you understand the language of physics. How many times in this room to this class have I said, stop and consider direction? Has it been a bunch? Okay, we're about to go into forces. Forces, for people who have never taken physics before, is one of the most difficult concepts we have. And it's going to challenge even some of the strongest of you in here. I would strongly encourage you to not minimize the fact that since we started this unit, I have always talked about reference and direction. What you will say later is, oh yeah, I forgot the negative sign. I will state is you never framed the problem. Frame your problems. It will make such a big difference in the future. So I'm framing my problem. I am deciding on direction. I'm saying up is positive, which means this is negative because it falls downwards 2 meters. This is positive because it's being shot in an upwards direction with an inclined angle. This is downwards because it's negative. This is negative because it's downwards. And this is positive because it's being fired in the forwards direction as I've indicated in my diagram. And yeah, I get the fact that the positives are unnecessary. The positives are there to remind me when I get distracted and have to come back to this, or I forget something, or I'm stressed on the test. They're to remind me that I thought that through and I'm ready to move on. It's just a simple thing to do to remind you that you have thought about direction. And it leaves no uncertainty to the person grading your paper that you consider direction. You kind of see what happens next, right? You can look and see whether you have 3 pieces on this side or 2 pieces on this side. We're going to try and find the time. The only way we can figure out the range is if I can take this and multiply by time. I don't have time, and I don't have enough things on the right to do so, but I have 3 pieces of information on the left. And you guys have done this problem before. Make it happen. I'll help you out. This is 2.5. But there's got to be a relationship that'll give me time. Now listen, folks. You guys are running off and working this problem. do this on your calculator. Learn to do it right now. I am foregoing the quiz today because I want you to spend these next few minutes knowing how to get the zero without having to try and remember what the quadratic formula is, and then all the stuff associated with it. This needs to be effortless and efficient. If you don't know how to do it by now, ask. I will walk around, I'll show at least one person at every table, and that person can show the rest. Figure out how to do this. And if you don't know what I'm saying, look, delta y equals 1/2 a t squared plus vy naught times t. Do you see how I've changed the formula to match the y's? Well, that's just going to be -2 equals 1/2 times -10 t squared plus 2.5 times t. So yeah, every one of these is probably going to have a quadratic that has to be solved. You need to be fast at it. So if you don't know how to use your calculator, do this super fast, find out today. Take the time. The quadratic formula is not part of this class. Finding zero is not part of this class, but you might have to do it. You see what I'm saying? So make it lightweight, make it easy. It's just too easy to type it in and have it spit out the zeros for you. So please, become good at it. We don't need the negative root ever for time. So time is always a positive number. It is possible to have a projectile problem that has two positive roots, right? This one has only one positive root, because the only other time we'd be on the ground is if we went back in time. It thinks that you could have gone back this way, but we can't, right? We're only firing it forwards. There is the possibility. So getting back to this problem, 90.93 seconds, correct? So 0.93 seconds, 0.93 seconds, right? The time has to be the same for both of them. Well, once you have got that together, your range is pretty straightforward. 5 cosine 30 is 4.33 times 0.93. I don't know what this is, probably 4 meters. We're pretty close, right? So that's where it lands. It lands 4 meters away from the edge of the table. Be cognizant of what you found. You did not find this, oops, what am I doing? You did not find this distance, okay? You found the distance along the edge of the ground to where it landed. That's the range. It's a horizontal distance. This is the basic problem. Everybody say, that's what I mean when I say the basic projectile problem is to find where a projectile lands. You can probably imagine that there's a wide variety of problems around this, right? Other ways or other things they could ask about. There are some things that are off the menu that they can't ask about because there's no mathematical way to find them. For example, for this problem, there's no way for me to say what angle would it take to strike the ground at 4.5 meters. And you may not understand why, but you should look into it. We will look into it a little bit later this week. But some problems are on the table, like, and I'm going to give you a selection of things you should be able to do. Ready? Thing number 1. No, let's move this over here, like that. You should be able to find out what is the maximum height. Not a hard one. We've talked about this one already. But again, just because it's a projectile doesn't mean it won't have problems that are not necessarily associated with where they land. If you're trying to clear a tree, the problem could be, does the object get high enough to clear the tree? That could be the maximum height. Now, max height occurs when Vy equals 0. In this problem, you would look for when Vy equals 0, and the question mark would be, what is delta y? Do you understand? You would not set the height to delta y. You would be finding delta y and setting Vy to 0, right? It reaches its maximum height when it's no longer traveling upwards. All good? Be careful. If you just do exactly what I just said, you will not get the right answer because the object started 2 meters above the ground. This just tells you how much y changed. But the maximum height would have to include these 2 meters, correct? So just be cognizant of the problem. Don't make silly mistakes because you're not thinking about the problem and you're just getting a numerical answer. because you're efficient at that. Always be thoughtful of the problem. The next clear follow-up is where along the ground? Bless you.
Thank you.
So where along the ground is the maximum height reached? That seems like a pretty obvious next step. It's clearly just related to what we just did, but again, it's an ancillary question. And for this one, same thing. You would set Vy to 0, but then you would solve for the time and plug that into the range. Right? This would tell you the horizontal displacement when the object has no y velocity. Are these ancillary questions making sense? Does it sound like stuff we would do? It's all stuff we've already done. But again, it is applied to 2 dimensions, not 1. You have to keep track of the fact that this thing is traveling in 2 dimensions at once. Be careful too. Does this object ever have 0 velocity? It has 0 y velocity, but at 0 y velocity, it's still moving, correct? So this object has always got a velocity. In fact, the minimum velocity is when it's at the maximum height. Little side thing there, keep that in mind. The minimum velocity is when it's at the maximum height. That has to be true because it's when Vy is 0. So the minimum velocity is when it's at the maximum height because Vy is 0. And there's always the clear and distinct possibility that they're going to ask you, how fast is it moving when it reaches the ground? Be careful. Be very careful for that question. Because if they ask that question, they're asking a trig question. If they ask you how fast the object's traveling when it reaches the ground, understand that when it reaches the ground, it's traveling at an angle, right? Something like that, which means that at that moment, it's got both the horizontal velocity that it had, and now it's got probably some different and larger vertical velocity. So I see 2 follow-up questions here. What is the velocity? The speed at which it hits the ground, perhaps, and what angle? Right, what speed and what angle? For that, I mean, you would have to consider the triangle that's here. And it's a pretty obvious triangle. But one of the things you would have to do is you would have to find Vy. Right? Vy when it makes it to the ground. Then you would have Vy and Vx. You could use it to figure out the velocity. This triangle isn't great, but I'll at least kind of put it together. This is what it would kind of look like. Right? Vy would be its velocity downwards, and Vx would be its horizontal velocity. You could use that to figure out V, how fast it's going when it reaches the ground. I'm thinking the Pythagorean theorem. And don't forget your trig. That's how you'd get the angle. But read the problem carefully. They may want the angle relative to the horizontal because they gave you the launch angle relative to the horizontal. So always be making sure you're being consistent. Does everybody understand the difference between those 2 angles? So put it in your notes to remind yourself, do they want the angle relative to the vertical or the horizontal? If they made their measurement relative to the horizontal, you probably should too. It doesn't change what you have to do here very much. It just means you're looking at a different triangle. I'm not sure I can take that one apart, but I'm going to try. There, I got it over there. It took me a minute, but I got it over there. So just make the different triangle of having two different times that are both positive, but it would have to be under a circumstance like this where you're shooting something up towards the top of a building. In this case, there'd be the time where you would pass that point on the way up and a time that you would hit it on the way down. That would produce two different times, okay? So we don't have to spend our energy tracing down negative times. I will have an aside where I redraw this just so we can talk about it for a moment. And I make use of something that you're all supposed to be experts in right now. And that's trig. Here we go, for all you people who need this. You should do the trig on this, right? You should be able to figure out what Vx is and Vy naught by looking at the trig. Considering this looks like the right triangle associated with it, this would be the opposite side, this would be the adjacent side, and it'll be like this every single time. So you guys who are pretty sharp should realize that it's probably true that this will always be how to calculate the horizontal component, because the horizontal component will always be the adjacent side when we're dealing with an object that is being launched relative to the horizon. And this also means that this will probably always be the vertical initial velocity, as it represents the perpendicular. Be careful, though, a little bit about vocabulary. This is considered the angle of, bless you, inclination. We say that the angle is inclined. That represents a positive angle of inclination. The word declination can be used to describe negative angles of launch. So if you see the word declination, then your initial launch velocity in the y direction is negative. It's downwards. So just be aware, inclination, declination. All right?